So let me begin by saying that the, the fundamental issue that lies at the core of my talk is the question as to what extent the basic quantum mechanical principles can be critically tested at the macroscopic level. This is the basic question that lies at the core of this talk. And here I should like to mention that this is the topic on which I had been working for the last many years. And my interest in this particular area, has been inspired by the interactions with Professor Anthony Leggett, whom I first heard giving a talk on this topic that may interest the students and young researchers to know way back in 1986 at a very special conference organized by the Hitachi company then, titled Conference on Foundations of Quantum Mechanics in Light of Technology. That was the middle of 1980s, and I had done my PhD in the early years of 1980s. In fact, mine was the first doctoral work on foundations. So that conference in 86 was a very big event in our line at that time, when this area was considered outside the mainstream of physics. And in that conference, Anthony Leggett, who is very well known and unfortunately who has passed away only recently, and so I dedicate my talk in his memory. So in that conference, and I was present in that conference, I had that opportunity, he first spoke about, and his talk was titled Testing Quantum Mechanics at the Macroscopic Level. And after that, of course, this line of research took a considerable time to develop. There were many skeptics after this talk, I remember, asking questions, why is this search important, and so on. So I shall cover some of those aspects in my talk. That I shall begin, in fact, by clarifying why it is important to critically test fundamental quantum principles at the macroscopic level. And now, over the years, various facets of this study have emerged. And in this talk, I shall concentrate on only one particular aspect of macroscopic quantumness. And in that context, what is the key element of our talk is of this work is the use of this quantum Zeno effect in the context of testing macroscopic quantumness. So I shall first begin my talk by clarifying to the skeptics and so on that why this line of research is important and why it is particularly important to test the sense of macroscopic quantumness, in which in this work we are trying to use the quantum Zeno effect. In fact, quantum Zeno effect is I shall also give a big background to the quantum Zeno effect. So quantum Zeno effect, this is for the first time in our present work, is being applied in the context of studying macroscopic quantumness. And so I shall explain why it is important to apply quantum Zeno effect, why it is useful to apply quantum Zeno effect in this context. So a major part of my talk, given the nature of the audience, I know from Prashanta, which will have many students and young researchers who are not initiated or who are not aware of this line of research, I shall give a very broad introduction to the basic motivation of this line of research, the various aspects of macroscopic quantumness that are being explored, and then I will zero in on the particular aspect of macroscopic quantumness which concerns our talk and the use of quantum Zeno effect. So I shall not go into much of the specifics of the details of our present work. I shall only try to give you a flavor of it, the basic idea, and why it is significant. So this is the plan of the talk, which I have already indicated. And this will be the introductory part of my talk. And the content of the talk will focus on using the quantum Zeno effect in the context of a very interesting scheme that was proposed by us in 2024, this work, where it was shown how quantumness can be critically tested. That going back to the Leggett's question that was raised way back in mid-80s. But this time, for this is where we made a jump from the earlier studies. This one was formulated for in a way so that it is amenable to be extrapolated for arbitrarily massive objects. And we had used a harmonic oscillating object in this context. So this work, which attracted considerable attention, and while Scientific American wrote an article on it, they titled it as Schrödinger's pendulum experiment. So in this talk, I shall refer to it as Schrödinger's pendulum experiment. And our present work provides a new twist to this, which makes it more easily experimentally amenable and overcomes some of the limitations of this work, including one of the limitations that was pointed out by Anthony Leggett himself after this work was published. And I will clarify this motivation later in the talk of using quantum Zeno effect, but the main message, so that those who watch will make up the mind of whether you will be motivated enough to listen to the entire talk, they can make up their mind. I'm indicating some flavor of the essential result of this work, that the motivation has been because this proposed experiment and all other experiments of macroscopic quantumness, the predicted empirical signature is always small. So how to actually detect it, and in the presence of decoherence, becomes very challenging. So it is fundamentally important to devise innovative ways how this magnitude of quantumness in this macroscopic context can be enhanced even in the ideal condition, and then you take into account the decoherence and so on. And this is the novel strategy we are invoking. So this has been my collaborators in the present work. They have been my collaborators, and all of them, apart from Marco Torres and Pritam Roy, were also involved in the work on Schrödinger's pendulum experiment, which provides the starting point for the for the specific example we will be considering in this present talk. So so I shall first give a broad flavor of what quantum Zeno effect is. And this is the historical connotation of quantum Zeno effect, which has its own significance. But the important point is that that historical connotation, this aspect of Zeno paradox, is different entirely from in what sense the term quantum Zeno effect is now used. By the way, this example has its own significance in the historical context, and also in the context particularly of the idea of infinite series and concept of limit and so on. And there's been much philosophical discussions about this formulation of the historical formulation of Zeno paradox. Now, what mean the pioneering work on quantum Zeno effect? It is a fundamental effect arising from measurement on quantum system. So the importance of this effect lies in that it focuses on a fundamental feature of quantum mechanics, which is related to the way measurement is described in quantum mechanics. All other fundamental features of quantum mechanics are the formalistic features or the interpretational features. And in the whole structure of quantum mechanics, the role of measurement is obviously very important, the way quantum mechanics describes measurement. And Mishra and Sudarshan pointed out this effect, which is quite remarkable, that quantum mechanics predicts that if you make repeated measurements of an observable on a quantum system, then you can drastically inhibit the evolution of a system. And in the extent of very large number of measurements, you can even totally freeze the system. So this was formalized by Mishra and Sudarshan in 1977, but they were mainly concerned with the mathematical description of a quantum theoretic description of measurement and several other formal aspects of this feature. But what later, and this paper was not much discussed or noticed, apart from these two papers in the subsequent years, and that was the time I had also started working on foundations from the beginning of 80s, as I told you. And that was the topic on which also we worked, and these two papers suggested also the possibility of empirically even testing this quantum Zeno effect. And the first experiment on quantum Zeno effect was done in 1990 by David Wineland's group. Incidentally, David Wineland is the one who did many pioneering fundamental experiments on quantum mechanics, include particularly the Schrödinger cat experiments. And this was one of his very interesting experiments. David Wineland, of course, won the Nobel Prize. So our work really provides a new twist to that Wineland group experiment in the macroscopic context. So that is the interesting. We develop a macroscopic analog of the experimental architecture used by the David Wineland group in showing Zeno effect for the first time. That is a remarkable experiment. I'll come to that. So the central message of quantum Zeno effect is that it illustrates what is called the invasive role of quantum measurement. That measurement described in quantum mechanics inevitably results in changing the state of the observed system. By the way, Mr. Chairman, you may remind me 15 minutes before the ending of my talk. So that
yeah, sure, sir. Please.
Okay. So this is the mathematical essence of quantum, the way quantum Zeno effect arises. I've given the simplest derivation, and that you can see that if you compute what is called the survival probability, the probability of the system being found in the initial state after a certain time, it evolves. And then if you follow, and then if you consider n such intervals, and if the time interval between two successive measurements is small enough so that it can be described in this way, then in the limiting case of n going to infinity, the number, one can show that the survival probability becomes 1. So to put it in a very concise way, frequent measurements, intuitive idea is that frequent measurements repeatedly project the state back to its initial form, effectively suppressing the evolution. And the first experiment which showed quantum Zeno effect is this one, and the idea is very elegant. One considers hello, there is okay. So the idea is that you consider, say, in that experiment, laser-cooled beryllium ions were considered, and what is important is that you drive any particular ion between these two levels. And these two levels, and this is a metastable level, and the radio frequency field drives transition between these two levels. And while this transition occurs, when the radio frequency field is on, so the system is evolving in time continuously. Then you do measurements by shining laser pulses. This is the measurement, and the way the measurement is done to find the survival probability that this ion is chosen such as it is that is the beauty of this experimental architecture. You have an excited level of the ion, and so then you switch on the measurement laser pulses of short duration, so that this ion at any particular instant you want to make a measurement how many ions are surviving in this initial ground state. Then you shine that light pulse, then the excitation occurs to this level, which is an excited level with a very short lifetime, so that the spontaneous transition probability is very high, almost 1, so that it immediately comes down to ground level, and the fluorescence photon is emitted. So by detecting the fluorescence photons, one can find out where those ions are in the initial state or not. Sorry. So this is the protocol, and in this way you perform n measurements during that, choosing an appropriate time. And then it shows that by increasing the number of interrogations, by shining the light pulses, you can increase the survival probability. Now, the example we will be considering to go to for formulating a macroscopic analog of this experimental architecture, that is the novel idea we have, that instead of going to this ion atom, you cannot one straightforward way would have been to go to macroscopic atoms, ions, but that is quite complicated and not, and the scalability is a big problem, so you cannot go to very large mass and so on. So what we have done is that to consider a harmonically oscillating object, and that architecture we have formulated for it by picking up on the Schrodinger's pendulum experiment we had devised earlier. That is the one that we will be using to implement quantum Zeno, and that will have its own significance that I will be discussing. Now, just a quick overview of the quantum Zeno effect. So after this 1990 experiment also took some time to attract attention, and then from the last decade or so, from 2008 onwards, so on, when it was first shown in this very paper, the use of quantum Zeno for protecting entanglement against decoherence. Then quantum Zeno, these are all the initial papers of the applications of quantum Zeno effect in these respective topics. So given the nature of the audience, I wanted to give you a broad idea about this. These are the representative works. And this is a very useful, up-to-date review, which has not yet been published. So quantum Zeno effect is a very vibrant topic of study at the moment. But you can also say, you can see historically, that's why I went into the history, that in the whole line of research in quantum foundations has been such that the fundamental ideas that have been were proposed and so on. It took considerable time to be developed, to attract attention, to motivate experiments and so on. Because the overall mood or the mainstream view was not very encouraging about the foundation. But now, of course, over the last decade and so on, things have changed a lot. So all those issues are being revisited with a lot of enthusiasm and new ideas. That is important, fresh new ideas. So it is an exciting time. And it is this context, this particular work, we have just finished. So let me first give you a broad idea about the motivation, the broad motivation underlying this line of study. So as I promised you, I shall first try to convince you why this line of research is important. So the macroscopic quantumness obviously relates to some of the fundamental quantum issues that remain unresolved even after 100 years. And of course, these are the two very fundamental issues. And of course, in recent years, these new ideas have emerged how you can use the fundamental quantum features, borrowing some of the ideas from the quantum foundational studies, can devise laboratory tests or what is now called tabletop experiments for quantum testing quantumness of gravity. But in designing these experiments, application, it is massive systems are used. So application of quantum mechanics at the macroscopic level has become particularly important also on this count. Now this next remark is what is very important in the context of the present work, that all these issues, for addressing them in empirically relevant way with available technology or near-term realizable technology, it is crucial to test quantum mechanical superposition of macroscopically distinct states of a macro object. So the macroscopic quantum, the sense in which macroscopic quantumness that will be tested in the kind of schemes I shall be discussing in this work is that aspect of quantum mechanics which concerns the validity of quantum mechanical superposition for a macro object. And in our studies here, by macro object where we mean massive object, that is important in all these experiments and studies concerning these issues. So testing superposition of macroscopically distinct states of a massive object, that is what is needed. And for this purpose, historically, that is Leggett formulated the famous Leggett-Garg inequality, which provides a key ingredient in testing this feature. And this inequality can be considered a temporal version. In our present work, we provide we are using testing macroscopic quantumness, so providing a slight twist to the original Leggett-Garg formulation, shift in focus. That I will explain. But before that, I have to explain to you what Leggett-Garg, what is the status of studies concerning this question. Just one quick remark, since last year this Nobel Prize was given for this macroscopic quantum tunneling. That was Nobel citation is mentioned. And these studies I will be concerned here is what is known as macroscopic quantum coherence. So the distinction between these two features was first pointed out by Leggett in 1980. In fact, the experiments for which the Nobel Prize awarded last year for macroscopic quantum tunneling experiments were inspired by this paper by Leggett, where he first emphasized the importance of critically testing certain aspects of quantum mechanics at the macroscopic level. And later he was some of the subsequent works, and that inspired experiments on this macroscopic quantum tunneling in the early 80s by John Clark and that other people you know, and which have got the Nobel Prize last year. But macroscopic quantum tunneling essentially tests that aspect of macroscopic quantumness, which concerns how collectively a large number of particles, like it could be, say, the fermions or bosons, like in the Bose-Einstein condensated boson, or in the experiments considered here, it is the large number of Cooper pairs, which show macroscopic effect, will give rise to macroscopically observable effect. In these experiments, they showed it for Josephson junction, tunneling current of a macroscopic magnitude for a large number of Cooper pairs tunneling. So it is the message of this study of macroscopic quantumness is to show that a large number of quantum particles can behave in phase to show a macroscopic quantum effect, which is macroscopically observable, significant effect. On the other hand, the macroscopic quantum coherence concerns testing that superposition of macroscopically distinct states in these two wells. So phase coherence between probability amplitudes inside and outside a single well play no role in tunneling. But in quantum coherence, this oscillating object between two wells, the coherent phase relation occurs between wave functions localized in the two wells. So if you want to test the superposition or quantum coherence between macroscopically distinct states of a massive object, the motivation is to devise schemes for showing MQC for massive systems. This aspect was first clarified in this paper, followed by Leggett's some of earlier some other papers, but gradually it started at attention, and that was the 1986 talk I was referring where he discussed all these works and the motivation for this line of study. Now, I have to So just to put things in perspective, since we are talking about quantumness, macroscopic quantumness, one may ask, or macroscopic non-classicality. So one should be clear about what is the benchmark one is using in this study for defining classicality, independent of the details of the formalism. What are the essential tenets of what we are calling classicality? And so that again we can test them against the basic tenets of quantum. So these are the features most of the audience perhaps know and they need know. On the point that I shall be, the aspect that will concern primarily in this work is this aspect of non-invasive measurability. In the classical worldview, you can in principle always consider a measurement to be non-invasive. That, of course, by measuring something inevitable, some disturbance, some error occurs, some uh, it will involve some effect. But in principle, classical theory, you can make those effects, you can control those measurement-induced effects and make them negligibly small. But in quantum theory, it is not possible, even in principle. I shall skip it just to give you a broad flavor. So this is the two distinct line of studies that has emerged. This is the PR-based study, you know, but that is based on testing Bell inequality. And this line of study was inaugurated by Tony Leggett. It is 88 and 85. He formulated this inequality with his then postdoctoral student, Dipankar, temporal analog of DR, and which is used now as a tool for testing quantumness of microsystems also in a very loophole-free way. But primarily the motivation was to use this for testing macroscope, that testing the validity of quantum superposition principle at the macro level. So I'm not going into further. So just to put things to a perspective. And here, the significance of testing quantum superposition for macroscopically distinct states of the measurement system was that it implies the violation of Leggett-Garg inequality, the temporal analog of Bell inequality. Like Bell inequality implies local realism, it involves macro realism, applying the concept of realism for the macrosystems. Now comes, and this to give you a broad idea what is the importance of testing superposition for macroscopically distinct states of a massive system. Show you my preceding talk was about Schrodinger type states. So here the focus in this line of research on Schrodinger type states, but for in the macroscopic context. And the particular macroscopic context considered is for massive system, because in these three areas of application, the massive system quantum superposition for macroscopically distinct states plays an important role. And what is very interesting is that recent years also, while this line of studies picking up attracting quite considerable attention, there have been also works emerging about possible applications of cat-type states at the macroscope for massive systems, for like what particular significance it may have for ultra-sensitive quantum sensing. This is just emerging line of studies. Now, just a quick indication of, I had mentioned that this is the importance in the context of quantum measurement problem. I will not go into the details of the measurement problem, but say that to describe measurement process, you have to apply superposition principle at the macroscopic level, involving the states of a measuring apparatus. And apparatus involve massive systems, massive devices. So system measuring apparatus combined state, if you describe measurement unitarily by standard quantum mechanics, this is the inevitable end product. And then this is not consistent with the emergence of a definite outcome in a single experimental run, because the different outcomes can be distinguished. But this is any particular apparatus is in a superposition of two states instead of being in one state or the other. But I shall not elaborate on the measurement problem. That is a much discussed issue, and various resolutions to it have been proposed. I am not going into all these discussions, but but this is one which is particularly important, which is attracted considerable studies, and this one. Now, this line of study considers the possibility that quantum superposition principle may break down for the massive system. So they give some parameters and bounds on the extent to which macroscopic superposition for massive systems can hold good. So the purpose of the study that I shall be talking about and is also to provide experimental constraints on these dynamical models of wave function collapse by critically testing the extent to which quantum superposition principle of macroscopically distinct states of massive systems can be extrapolated for massive systems. Also, this line has implication for Bohmian model, but that will require some discussion, so I'm not going into that. So that is already I have mentioned here. So this is the empirical constraints this study will provide. And there are different types of dynamical models of wave function collapse, the way quantum mechanics. So the idea is that when you can describe measurement process for massive systems, this wave function collapse you can describe by adding nonlinear stochastic terms to Schrodinger equation. There is also the idea of the Penrose idea of how gravitational induced collapse can occur, but that also involves the possible breakdown of quantum superposition principle at a certain level, and that also arises from superposition by applying superposition for macroscopically distinct states. So for historically, so after 1985-86, Leggett-Garg inequality has provided a powerful tool for this purpose, and it may be of interest to know. So this opens up the exciting avenue of experimentally testing approaches to the quantum measurement problem, which was earlier considered to be only a philosophical problem or conceptual. And there's a lot of debate about it, and even in recent years, tests of specific models of wave function collapse have also been performed. But I'm not going on to elaborate on these aspects and instead go over to the next. So, and also I make a brief remark about the way macro superposition in recent years is now used for formulating schemes for testing quantum gravity. Shogato Bosch already gave a talk in this conference, so you are aware of the basic. I shall only remark that what is interesting is that testing the quantumness of gravity in the small curvature, low energy limit using laboratory-based experiments essentially exploits the fundamental quantum features, and thus the schemes that have been devised for this purpose is testing both these schemes involve applying quantum mechanics for spatial superposition of macroscopically distinct states. You take two massive objects in parallel interferometers and make them gravitationally interact, and then try to detect the gravitational induced entanglement. So the fundamental quantum features, the foundational features, are used for testing quantumness of gravity at this low energy limit, even for the small curvature. And it is predicted to result in observable signatures. And this was the work done in first work. And then in recent years, we have been involved in this work where we focused on, here the focus was on testing quantum entanglement generation as the signature of quantumness. Here in this work, that is in more line with the present work I'm discussing here, is focusing on that quantum aspect which is related to the measurement induced disturbance. So if gravity is quantum, then its measurement will result in inevitable disturbance. And this scheme we had proposed to detect it. But for the purpose of this work, of this present work, what is important is to note that superposition of our macroscopically distinct spatial states of are critically involved in all such states. So devising such, so before testing of quantumness of gravity, it is also important to test efficiently and decisively the application of superposition at this level. Hope by this time I have convinced you about the importance of testing all these aspects of macroscopic quantumness, and the various approaches I have summarized here to give you a quick overview and the experimental status at the present time. So this is the type of studies that have been, perhaps many of you already know, the experiments done in the matter wave interferometry. The other line of, but the problem is here for scaling up these experiments for much larger muscle. Only up to this point it has been realized. But what also the other line of study has been that scaling up the Stern-Gerlach interferometric test, which can also critically test quantum coherence. But for that, this kind of tests, a formidable challenge is that not only, is to recombine the beams emerging from the Stern-Gerlach setup in order to show the quantum coherence effect clearly. You have to recombine to create the original to show that the coherence, to show the evidence, to evidence the coherence present in this whole experiment. And this has been realized only up to this level, and the scalability is a problem to us. Although there are schemes proposed, how this recombination problem can be either avoided or addressed. There are also proposals for testing both spatial and spin properties and so on. And also a lot of work now going on in devising an alternative to Stern-Gerlach setup. One can devise setups to show quantum coherence, which also can produce the macroscopic superposition as well as certify its coherence, like Stern-Gerlach does. It can produce a macroscopic superposition of states and then certify its coherence if the beams can be separated beams emerging from the Stern-Gerlach setup can be recombined accurately. But that recombination, precise recombination, is a formidable challenge. And the other, that more dominant line of study over these years have been that using the Leggett-Garg inequality and its quantum violation demonstrate macroscopic quantum coherence. While a lot of applications of Leggett-Garg inequality have occurred even at the microscopic level, because it has been used as a very powerful tool for also certifying quantumness at the micro level, and has given rise to have an application in the context of reliable random number generation, the work in which I was involved with the Urvashi Sinha group. And in our talk here in the same conference, Urvashi Sinha had talked about this application in the context of randomness generation. But this is interesting that the inequality, which was originally formulated for the purpose of testing macroscopic quantumness, has also found applications in the microscope. But in the macroscopic context, what is the status of Leggett-Garg? On superconducting quantum interference devices, there this quantum superposition has been tested at the level of 10 to the power, say, 15 electrons circulating, oppositely circulating currents of this, circulating in opposite directions in a squid ring. So there's an oppositely circulating supercurrents, the coherence between them. The other remarkable experiment at the macroscope. Here the macroscopicity parameter is the current, or you may say the difference in the magnetic moments of the two oppositely circulating supercurrents, which is quite large compared to Bohr magneton lens. The other length scale over which it has been macroscopic scale is distance. There, the coherent oscillations of neutrinos have been demonstrated and the violation of Leggett-Garg inequality over that distance scale. The photonic interference experiments where the separation between the photonic paths much larger than the wall length. That is also in some macros. So the point I'm stressing here that the macroscopic context can be different in different experiments. So in what sense one is demonstrating macroscopic quantumness should be precisely defined, like I show also in the case of macroscopic quantum tunneling. Because many of the reportings after the last year's Nobel Prize did not sufficiently clarify that aspect. So one may ask that after this was shown, why the need for testing macroscopic quantumness? However, so to date, but what is important is that no experiment has been done to show macroscopic quantumness using Leggett-Garg for massive systems. And the idea of how Leggett-Garg inequality can be applied in the massive system was first given by this work, which I mentioned earlier. But it is the smallness of the observable signature of macro quantumness that makes it difficult. So I think I have now 15. Mr. Chairman, how much more time I have? Hello? Hello?
Yes, sir. You have about 13 minutes.
Okay. So
I think you are
have
well
I
within
been
time.
okay? So have I been audible throughout? Because
Yeah,
is it
you have been
okay?
audible, sir. Yeah.
Okay.
You're very much
Okay.
audible.
Any problem? Because now I'll come towards the end of my talk. So the key
Yes,
question
please.
we have addressed that how we can enhance or amplify the signature to facilitate its experimental realization. And the basic idea I have to first recapitulate the basic idea of the pendulum experiment as a linear harmonic oscillator prepared in a Schrodinger coherent states. And then that is the interesting idea we had invoked, that instead of considering precisely defined dichotomic, we consider coarse-grained spatial measurements to determine the dichotomic measurements. So we dichotomized it. It's a continuous variable problem, but we dichotomized it by considering coarse-grained spatial measurements which determine which half of the harmonic wave the particle is, so that we can use we discretized the description, and then we could use the two-time Leggett-Garg inequality. But all the earlier formulations of Leggett-Garg inequality inspired by the Leggett's original work, they had considered same observable at successive instants and the temporal correlations between them, which is the bounds on the temporal correlations given by the Leggett-Garg inequality. Like Bell inequality gives bounds on the spatial correlations. But here we considered in this Schrodinger's pendulum two different observables, how their measurement at successive instance can also lead to various violation of Leggett-Garg inequality, but importantly in a way that can be scaled up for large mass. The violation which remains same for whatever be the mass. That's why we call this scheme mass independent scheme for showing macroscopic quantum coherence. So I'm not going into further details. Only mention that you forget all the details. If someone asks, I can tell you, or someone can see the paper. But the main point is that the violation of Leggett-Garg we get in our earlier formulated setup, although independent of mass, was 10 to the power minus 2 order. So that has done, and the candidate systems for this purpose that were considered the oscillating nano objects of mass, say 10 to the power 13 or 14 atomic mass unit, massive nano objects that are levitating massive nano objects, which are now experimentally being realized. This effect remains too small to be detected with the present state of technology. So in our present formulation, we consider successive measurements performed within the same half of the oscillation region, and we consider all the measurement outcomes, whether they are detected outcomes or negative result. You are shining light in only one half of the, just to give you an idea, this is the setup, and it's an oscillating object, and you shine light only in one half of the region, and you make repeated measurements at various times. Then it falls under the quantum Zeno framework. You can, like the way I already discussed, you do repeated measurements. You see how it is, in what sense it is a macroscopic analog of the David Wineland experiment. David Wineland, it was ionic transition between, it's an oscillating transition between two levels. In this case, it is oscillating between two regions, spatial regions. And then the interrogations, there it was done in terms of by shining laser pulses, and then detecting fluorescent photons. Here it is directly done by shining light in only one particular region. You begin the objects, and this we call the survival, the probability of finding in any particular region. So if you just focus on probability of finding the particle in any particular region, then that probability is affected by the number of successive measurements. And one can show that this quantumness effect, that is the increase of the probability, survival probability, is significant enough even for large mass. So successive measurements are considered, and so one can compare the probability of obtaining the system at the initial state without intermediate measurements and with intermediate measurements. And this is the parameter one can define. Then for classical systems, this parameter should be vanishing because there should be no disturbance. One can ensure the disturbance if one designs the experiment so that the classical disturbance, or you can compute because it is shining light pulse, so you can calculate or determine what is the pure classical disturbance. I shall mention that point briefly later. And then the quantum disturbance, if you quantify, then this will be evidence of measurement-induced quantum disturbance. And we are again here, we take the coherent states, and why coherent states? Coherent states are now experimentally prepared for this massive nano objects and so on, and also ground state cooling has become achievable. And also it is conceptually important because coherent states show the classical like behavior. So you're showing even for massive systems quantumness of the most classical like states of quantum mechanics. So the basic idea of protocol is to evaluate this parameter and compare this to survival probabilities with and without intermediate measurements. And it depends on these parameters, initial peak value of momentum, mass, and the time of duration. All can be chosen. And it is important, the experimental challenge is that you would have to have low temperature because the coherent state mean energy has to exceed the thermal energy. So these constraints can be satisfied, and because already nanokelvin temperatures have been reached for large, in the LIGO experiments, the quantum gravitational wave detectors, oscillating mirrors have been designed.
Excuse me, sir.
Hello.
Sir, you have 5 minutes left, sir.
Okay, I know. So these are some of the experimental details, but what is important, I give you an idea of, say, how this is the coherent state parameter. You prepared the states. This is the disturbance parameter, I may say, which is zero pure classically. By increasing the number of measurements, you can increase this disturbance parameter. And you see the quantumness is evidenced by the non-vanishing value of this disturbance parameter, and it is of the order of 10 to the power minus 2, whereas in the earlier experiment it was of the order of 10 to the minus 1. But this enhancement is achieved only by, even if you do just merely 30, and the type of setups are now being possible with, one can do experiments, and that I will come, that I will indicate. If you take a diamagnetic trap and you consider oscillating nano objects of that large mass, if you keep the time of duration 1.5 seconds, it is possible to choose the number of intervening experiments up to 160, and the coherence time here can be appropriately kept small. So all those details are there, which makes this proposal having significant near-term realizability and can be scaled up to using with 10 millikelvin cooling and 1 hertz and measurement time, as I already mentioned. You can go up to significant value, achieve significant quantum, the significant signature of quantumness at that level. Now, the specific experimental systems that are being considered for realization of these proposals that are possible with the present state of technology are these two systems, which have been ground state cooled and all these levitated nano diamond objects and 10 kilometers. These are two remarkable experiments which had opened up a rich avenue for experimentally probing macro quantumness. Really new frontiers are emerging, and this particular proposal can be useful in the context of both these two systems. But one point only I want to mention, that one may wonder that, okay, I'm talking about that scheme in terms of interrogating it in terms of repeated shining of light pulse. You may say that quantum, and then we compute how the survival probability gets affected by that measurement. But that shining of light will also involve classical disturbance. So how do you calibrate the classical disturbance to identify the part which is really inherently quantum? So that was the challenge that when we first conceived the idea of the Schrödinger's pendulum experiment, that challenge was pointed out to us by Anthony Leggett while we were interacting with him, and he showed keen interest in the Schrödinger's pendulum experiment, then how to take it further. So then this is the idea we came up upon, that you can design a control experiment, the control by preparing a vacuum state for as a control run, and there you do the same measurement protocol. Now this vacuum state has a significance that it remains unchanged under harmonic oscillator, and symmetric coarse grain position measurements we are considering do not give rise to any quantum disturbance. So this control experiments ensures that a quantum disturbance is not predicted there by quantum formalism, but whatever disturbance occurs there must be classical in the same experimental context. And then you consider the initial coherent state preparation to be different from the vacuum state that we are considering. That means really taking the initial Gaussian state peak to be at the center or not. So, and then you do that experiment, our really signal or running signal experiment as we call it, and the parameter we determine there will have both quantum and classical contribution. So you subtract and identify the quantum part, whether the corrected signal exceeds the classical baseline. So we are grateful to the late Anthony Leggett for the useful interactions which led to this idea. And I have indicated physical, and these are the three. So I hope I am on time. Okay, so these are the three possible lines in which the further follow-up to this work is being pursued. But there are also other possibilities. So thanking you for your patience, and I look forward to your questions if time permits.
Thank you, Professor Dipankar. It was a very interesting talk, and I was very happy to hear the name of Professor E.C.G. Sudarshan also in this talk, around whose idea this talk actually revolved. I think that was great. And there were lots of new things which I learned. I mean, for the first time, I heard about massive Schrödinger pendulum. And then I have one question, that this massive pendulum,
please.
can it have masses of the order of, say, kilograms? And still show some kind of
the experiment, I may tell you, as I have shown, these are the two candidate systems which I mentioned. Uh, uh, and after the Schrodinger's pendulum experiment paper came out, so as we have been exploring, so these are the two candidate systems out of this. After this experimental works, and our paper was published in 2024. So and one of the collaborators in our paper, Henrik Ulbrich, is a leading experimenter in this nano object, levitating nano object, what is now called the optical levitodynamics. That means optically levitated nano objects which are oscillating, and they specifically use nano diamond crystals of this mass. And low noise, these diamagnetic traps are useful to cut down, and also the required low temperature, less than millikelvin, 10 millikelvin, and all those vacuum of that order 10 to the minus 10 millibar and so on, to cut down all the other uh, undesirable scatterings and so on. So that have been achieved. So there's a distinct possibility of realizing but then the problem has been this low magnitude of the predicted quantum effect. So that is what we seek to circumvent by this use of Zeno effect, the experiment that I right now discussed. So that is what
precisely.
Yes, that is
will
address.
Precisely the title of your talk also, in fact.
Yes,
And
yes.
That was really very interesting.
So now
there is one thing more. There is one thing more, Professor Dipankar, which I was getting in mind. As I come from a community of teachers, in the country under Indian Association of Physics Teachers.
Yes.
And we have, been running last year lots of programs to celebrate International Year of Quantum Science and Technology. We also have a journal called Physics Education.
Yes,
I believe
I
that
know.
Yes, there are lots of talks which have happened in this particular program.
Yes,
and I really like the way you have placed your talk for a lay audience also. I would request that if we can really have these talks published in our physics education journal at a level where now at undergraduate level, at a PG level, very many people are asking why we are talking so much about quantum science and technology, and what is there to do in it. I mean, that is where I would really love that IAPT and this kind of a group come together to do something. And I would like to, I'm very happy to also inform you, sir, that lately we have also brought out a network of quantum science, engineering, and technology. And we are calling it as Network Quest. And this is an initiative of IAPT only, in which we would like to really have good lectures, for an audience which is very much interested in learning about these new things, some workshops, etc. So since you are one of the leading quantum scientists of the country, I would like to really request you that you please help, and maybe we will invite you for a lecture to talk about these possibilities which are, there for our students to really catch on. Because sometimes people say there is a lot of talk of quantum mission going on. Where is that small cake for people who are in educational institutions? How can they really become part of it? These are some questions which are being asked by the community time and again. And I really loved your talk for that matter. Even when I was hearing Professor Sanjana Ghosh's talk, it was a very interesting talk. And one could relate these things and maybe bring something which is not formally found in textbooks, but can really come in this particular fashion.
Yes. In fact, thank you very much. In fact, that is precisely I had in mind in planning the talk, since Prashant told me that there will be many undergraduates or students, so at least they can get a flavor. And also a lot of questions now asked after last year's Nobel Prize also. interest
Yes,
about
yes.
macroscopic quantum tunneling. Now, so what is really the significance of that work, and why also these studies are being done? And this is now an emerging frontier. And I
Yes.
may tell you that one of the last interactions I had with Anthony Leggett, he was jokingly, we were thinking that quantum 3.0 could be the harnessing macroscopic quantumness, some new
Okay.
distance of technology kind of
Yes.
because
And in fact, I was very much, happy to see your acclaimed books. I was not knowing about these books also.
okay.
And what we are doing in Indian Association of Physics Teachers, I would request you please our website. We have
Yes.
brought out a web page on which we are, hosting certain books in their PDF format, free of cost to the community. If we can really do something of that sort also, I think we would love.
Yes, I would
that.
love to, because that book Conceptual was written in 1997, the first book at
Yes,
that time, when it was with Leggett's forward, and the other book has Penrose forward. That was also could be of interest for the white section, a reappraisal of Einstein's struggles against quantum.
Yes. And
So
sir, let me tell you
both
that.
the PDFs are available online now. So I think there should be no problem in uploading them.
Yep, please, sir. If you can share those, I will put those in our book.
Okay, I'll be in touch with
also.
you. I'll be in touch
Yeah.
with you, and I thank
and
you.
I would
Thank
like
you very
to
much.
really thank Professor Prashanta Panigrahi, sir, that he made me come to this session and listen to wonderful talks. I hope we will have more such interaction in future via our network of Quest itself.
Yes.
And if there are any more questions which participants would like to ask, you are welcome. I think we have some lunch time to squeeze these questions in between. Any questions, please? Yeah, Nilesh, please switch on your mic and ask.
Hello, am I audible?
Yeah.
Yes.
Yeah, right. So I had one difficulty in kind of grappling, because the quantum Zeno effect is basically, in some sense, saying that the system becomes frozen in its initial state if you perform a lot of measurements in the limit of infinite measurements. However, in that Zeno enhanced Schrodinger's pendulum experiment, where you have shown enhancement of the NDC violation, it seems that performing repeated measurements is actually increasing the violation. So, in some sense, intuitively, I'm having a feeling that maybe it's kind of counterintuitive to the original kind of implication from the Zeno paradox, that the system remains frozen in its state. So, like, what am I missing here that kind of joins these two things?
Historically, that was the aspect that was emphasized, that freezing of time evolution of the system. So the focus has been shifted from that original focus of this Zeno effect. Here, really it is quantifying the parameter kappa, the effect of repeated measurements on the violation of the non-disturbance condition. Let me put it that kappa parameter quantifies this kappa NDC parameter. You see this with the subscript.
Right, it's like the difference between the survival probabilities with and without
intermediate. So this is the parameter quantifying the violation of non-disturbance condition. And the non-disturbance condition is the classical condition, that measurements, there is no quantum disturbance occurring due to the measurement. So how do you quantify that effect of repeated measurements, quantum effect, that you quantify through the value of this parameter, chi NDC, after repeated measurements. So the inspiration is from the original formulation of the Zeno effect. The basic idea is that to use the role of non-invasiveness of quantum measurement. And then,
So kind of rephrase, I was asking like how is performing more intermediate measurements kind of increasing the violation,
because
the NDC value?
the violation increase because without intermediate measurements you have a certain value of the survival probability, and as you increase, this is the parameter. So to make this whole thing quite large, you need to increase this chi value or decrease this value, or you choose where the survival probability n equal to 1, you just get it. So it is by increasing this value of kappa, the way the survival probability is affected, that due to repeated measurements, you enhance the whole parameter. So the basic idea is that when you do repeated measurements and this kappa NDC, this parameter gets large as you increase the number of n. And how is kappa NDC defined? By comparing with the case with no intermediate and with intermediate measurements.
So thank you. There is another hand raised. Mr. RS, can you please ask your question?
Yes. Yeah. Thank you for a very interesting and informative talk. I have two quick questions. If I understood correctly, you have considered unitary evolution. So if you introduce decoherence, so in will you see robustness of quantumness in pendulum experiment? This is the first.
That is a good question. Good question. Yes. And your second question is?
Yes. Second question. In one of your slides, you have mentioned quantum sensing and quantum metrology. So question is, what kind of benefits one can expect from quantum Zeno effect related with quantum sensing, quantum metrology, and also I think cat state you have mentioned. So could you please?
Now that your first question is very relevant, as the original that Schrodinger's pendulum experiment we formulated was, and the experimental conditions were being chosen for the massive nano objects such by keeping all the temperatures and oscillation time and so on, so that for those specific systems considered, which are now feasible to be experimentally implemented, like those 10 to the power 14 atomic mass unit oscillating nano objects, in those kind of situation, the decoherence and other factors with the kind of vacuum and with the kind of low temperature cooling that is achievable, they can be kept at a negligible level. So those computations were done for those kind of decoherence effects that are considered for the mass range, for the specific objects like the levitating nano objects, the nanocrystals, nanodiamonds really, of that mass, 10 to the power 14 atomic mass units. That already those studies have been reported. That is the Henrik Ulbrich group and their literature. So those decoherence studies and the parameters chosen for coherent experiment are such that the effects of decoherence do not affect significantly. The actual and quantitative computations have been done, not reported yet, but they can be kept negligibly small. They are controllable. So that's the effects. But the problem is that to control those decoherence effects, the problem that what experimenters have faced is that there are certain challenges. So it turns out that it would be useful to enhance in itself the magnitude of the quantumness signature. Then the decoherence effects are much negligible compared to the observed effect. That's why use of Zeno effect, precisely, so that the decoherence effect can be ensured to be sufficiently small. That is still not possible with the original Schrodinger's pendulum experiment. With the systems I talked about, particularly the 10 to the power 14 AMU massive nano objects. The 10 kg mirror case, they have done extensive decoherence studies because it is used for gravitational wave detector. So there an advantage of a sufficient control of decoding, but still applying our set that in the Schrodinger pendulum context, even taking that mass, the effect, the magnitude of the effect remains smaller, quite small. So Zeno, the use of Zeno may also quite considerably help there to make the effect striking. About the sensing application, it is only at a there are some papers available and so on, you may contact me. But I have not yet looked into it sufficiently carefully. This is being talked about in the literature, and there are papers, especially about the possible applications in the context of the gravitationally induced entanglement.
Thank you. And you are, please, you have raised your hand, ask a question.
So,
yeah.
Thank you, Professor Dipankar Home. So this is, I just wondered if one can focus on the different types of measurement. For example, quantum non-demolition measurements are some weak measurements, and study the kind of different aspects that one studies by focusing on the different types of measurements involved itself. For example, in LGI, suppose I have two sequential measurements. Suppose I use what is called as compatible measurements. Whatever may be the dimension, I will not find any violation.
Yes, that is a whole area not yet investigated. In fact, we considered only this project course in that kind of measurement projecting. It is to begin with, to just launch this line of study. But then also we considered coherent state. So now subsequent studies have been done with some of my collaborators already on using mixed state, thermal states. There were lots of questions like what happens, we considered coherent state, what happens if we start with mixed thermal state and so on, which is more common in actual experimental context. How robust is this predicted signature of macro quantum? And this is whole area you have rightly pointed out, where you can use different types of measurement, POV, and different types of measurements. It is a whole area.
Thank you.
Oh,
Thank you.
That many interesting questions. And it's fresh ideas fresh ideas are needed. So that in the macroscopic quantum, you can, even the kind of work you did with the role of unitarity. So whether one can play around it and say, try to explore to what extent unitary quantum, apart from collapse, quantum unitarity to what extent is valid in them. So all it is. That's why Leggett used in his last years were using the phrase quantum 3.0. Possibly.
Thank you.
So, are there any questions? Any more questions?
Yeah, Professor Alwal, I just wanted to add, this quantum Zeno effect. Since this conference being held in Odisha, the co-author of this quantum Zeno effect paper with Sudarshan was Professor Vaidyanath Mishra from Sambalpur.
Yes.
And you'd be surprised to know in Odisha particularly, I checked with students, nobody knows he is from Odisha.
Prashant, thank you very much. In fact, I should have mentioned it. I keep myself.
That's fine.
It didn't. I had planned it, but missed mentioning it. Oh, thank you so much.
Thank you.
In fact, I was pleased that, and I had the opportunity of meeting Professor Mishra at a conference in 1987 in Athens. I remember Schrodinger equation centenary, and as I was telling him that I have worked on this. And he knew me because we had by that time worked on the Zeno effect. So he was asking me at that time, it's very unfortunate the people are not noticing this thing, and it may have so features. I'm so happy you did this at this stage, and he was quite lamenting this feature.
Professor Dipankar and Professor Prasanta, I would like to tell you that last year when we were celebrating this quantum year, we also brought out a special postage cover highlighting the work of Indian quantum scientists. And we had made sure that Professor E.C.G. Sudarshan's picture is on that particular cover, because very few people know the kind of work which people did, Professor E.C. Sudarshan did. And he was deprived of a Nobel Prize, actually. I would put it like that, both for VA theory as well as for quantum optics itself. So our effort is to bring all these stories to the knowledge of our community, because that is what is our role in Indian Institution of Physics teachers. Yes. And that is why you will find that even we were talking with Professor to revive one journal. If there are students sitting here in this audience, we have one journal which was initiated from Odisha only, called Prayas. Professor Satpathy was actually the one who really started it, and we call it as a student journal, where students can send their papers and publish their work when they are doing some small projects, etc., etc. Also,